Okay, so we're going to do some multivariable calculus. I'm going to find the Gateaux differential, which is noted like this, of this functional here. So from 0 to 1 dx, square root of 2x squared plus 2y squared times the square root of 1 plus 2y prime squared. And the formula for working out the Gateaux differential is this intimidating looking equation here. We've got derivatives and epsilon h introduced, epsilon equals 0. I'm going to explain that to you what that means in a minute. First of all, to note that this is a functional, so it's a multivariable calculus. So it's with x, y which is a function of x, and we've got y prime which is a function of x. So we've got everything going on inside here. So how are we going to go about finding this? Well, first of all, we need to go and find this. So s of y plus epsilon h. So let's transform this equation here with this formula here. So s of y plus epsilon h. So the parameters of integration stay the same. And now we introduce epsilon h wherever we see a y. So 2x squared, we don't need to do anything for that. 2y squared, so with the y we need to write as y plus epsilon h, and that is also squared. Okay, so this is getting to look quite a big equation here. So we've got a 1 plus, and then a y prime. So the y prime result, the rules still follow the same as with the single y without the differentiation. So y plus epsilon h, we'll have a 2 y prime plus epsilon h prime all squared. So that's where our functional is now, with epsilon and the function h included. Okay, so now we need to take the derivative with regards to epsilon. So s of y plus epsilon h, and actually just put the derivative sign in front of that. What we do now is take the derivative of this with regards to epsilon. So to take the derivative of this, first of all, we can bring the derivative of epsilon h inside the integral because epsilon is independent of x, so that allows us to do that. So now we're left with a good old basic product rule. So remember the product rule. So we've got two functions, for example, let's say d and f. Let's just rewrite that a little bit better. So we've got two functions d and f. So that equals d prime f plus d f prime. So if we're going to make this function here our d and make this function here our f, and then we'll take the derivative of each one. So first of all, let's rewrite these into much easier ways to take the derivative of. So if I let our d first equal 2x squared plus 2y plus epsilon h squared, and then that is all to the power of 1/2. Okay, so that's our d. So now let's take the derivative of that. So we can subtract that by 1. So now we end up with that in the denominator. So the square root goes into the bottom. So I'll just write that down as the square root now. So that's 2x squared plus 2, let's just put that bracket back in place there, 2y plus epsilon h squared. So that's with that there, and then we'll have an imaginary 1 at the top, I suppose, and then a 2 there. So that's our half. And then now what we need to do is, by the chain rule, take the derivative of y plus epsilon h squared inside here. So we'll have 4y plus epsilon h. So let's get rid of that y, just write 4y plus epsilon h. And then again, multiplying by the derivative of epsilon inside here, which is just h. So that's our d prime. So now let's rewrite our f function for f, which is this one. So let's just rewrite that as 1 plus 2 y prime plus epsilon h prime squared, and that's to the power of 1/2, i.e. because it's the square root. So same as before, our f prime, that's going to be 2 square root of this, 1 plus 2 y prime plus epsilon h prime squared. And as before, we take the derivative of this and put that on top. So we've got 4 y prime plus epsilon h prime, and then the derivative of this as well, which is going to leave us with h prime. So now what we're going to do is use our derivatives and our functions, and let's work on this. So d prime f. So d prime f, so that's 4y plus epsilon h times h, 2 times the square root 2x squared plus 2y plus epsilon h squared, and then we're going to multiply that by our f, which is this one, which is basically the square root of 1 plus 2y prime plus epsilon h prime, and that's all squared. And then we're going to add to that, so I need the second line here. So now we've got d and f prime, so it's this one. So actually let's write the f prime one first. So 4y prime plus epsilon h prime times h prime divided by 2 square root 1 plus 2y prime plus epsilon h prime, all squared, and then this function on the top, which is, so if I just write that as multiplied by the square root 2x squared plus 2y plus epsilon h squared. Okay, that's a pretty intimidating looking equation there. A few little simplifications we can do. We can just get rid of these and they can then become just a 2 in the denominator. So that's fine. The rest of it, I'm just going to leave it how it is for now, because the next thing we need to do is take the limit as epsilon approaches 0. So if epsilon approaches 0, this is 0, this is 0, that's 0, that's 0, 0, and that's 0. So let's rewrite it down now. Let's write s of y comma h. So we can put that as our Gateaux differential. Okay, so 2yh, and this one is square root 1 plus 2y prime squared. So that will take care of the numerator on this function here. And then the denominator, we're going to have the square root of 2x squared plus, should have put a bracket in there, plus 2y squared. Okay, that takes care of that one. Can't see any more we need to put in there. And then we can add. Let's take care of this one first. So 2y prime h prime. Let's put this denominator in, as we're there on the page there. 1 plus 2y prime squared. This one disappears. And then in the numerator here, we can put square root of 2x squared plus 2y squared. Okay, I'm sure we could make that into a one fraction, but I'm going to leave that to you guys. But that would be a suitable answer for the Gateaux differential. Okay.